Okay, good morning, everyone. As Louisa said, my name is Dalton Lunga. I'm a research scientist at Oak Ridge National Laboratory. It's my pleasure to be moderating a panel that consists of three experts that are really putting to use cloud-optimized formats and deploying these on different use cases. So to kick us off, the plan is for me to set the context. There are three things that I would like to highlight. The first thing being what it is that we mean by cloud native formats, cloud optimized formats, and what makes this this type of technology challenging to adapt as we are moving from the traditional file formats. And then the last point that I'll highlight is on the different types of formats, of which I won't say much, given that the three use cases are actually going to demonstrate how these formats are being adapted in real use cases across different applications. So geospatial data, if you've been working with it, for quite some time, one thing that's been evident is that we are increasingly collecting a lot of this data. So the size and volume is growing exponentially, but not only that, the complexity that comes with the data as well is increasing in different dimensions. So what's been evident as this increase in volume and complexity have been going on is that traditional methods that we've been using to access the data sets, they're not scaling, or they're not actually proving to be optimal for a lot of scientific use cases. So as a result, we are starting to see a migration of the cloud ecosystem moving to some of the technologies moving into the cloud ecosystem to take advantage of the cloud architectures. For example, distributed compute storage, to make things easier, because at times when you build applications, you don't want to have all the data with you. If you have applications where you actually need to have large volumes of data, the pain is that you have to wait longer to download. So if you want to efficiently prototype or even deploy solutions on specific AOIs, the question is, can you do that in an optimized way where you only have a partial access of what the data that you need and then inform your application? So as I mentioned, three things to highlight. What do we mean by cloud optimized? The first part and the motivation is that these are file formats that are allowing users to have partial reads. You don't have to read the entire files. You only index areas where you are interested in. So the partial reads can be executed in parallel ways by taking advantage of the metadata that allows for you to index portions and not the entire files, but only portions of the data that you need to use. And what that then enables is that for those that are doing analytics in the cloud, for example, if you're using some of the computing engines, distributed computing engines like Apache Spark, that allows for you to have in-memory storage of the data, whereby you can then execute things in a lazy fashion by only retrieving data just as you need to do the computations. So that seems to be really circumventing this issue of having to pull all the data and have it within your local storage. So the latence that you often run into with the file downloads is mitigated by adapting these cloud optimized formats. So why is that becoming a big technology to migrate to? Whether you're from a provider side or you're from a user, the benefits varies. Some of these benefits we'll hear in the context of the different use cases. I mentioned the latence, less storage requirements. If you're on the user side where you deploying things on the edge, you may not have enough storage, to store large volumes of data, of which your applications may not need the entire data set, but just a portion. So the cloud optimized formats allows for you just to get what you need for the applications that you are deploying at a given time. And then from a provider side, it's less downloads. It also helps to even enable a broader access to the data sets that different users can get to. On the emerging opportunities, I mentioned Apache Spark, Apache Sedona. There's a lot of cloud computing, distributed computing engines that are then helping to minimize, some of the deep dive that would be required, because all of these technology, once they optimize and prototype and they're available in the cloud, users can leverage the back-end implementations without having to reinvent the wheel by themselves. So what makes these file formats to be challenging to work with? So two things to highlight here. First of all, geospatial data comes in different forms. Some of it's imagery based, from your satellite imagery or other forms of collecting imagery data. And then some is in point form, vector data sets. So the question is, if you have to optimize all these file systems, can you come up with a consistent way in which all the information can be aligned? That's a huge question. If images are collected at different resolutions, that's not an easy answer, to align, things that are collected at different scales. Say, for example, you have your very high resolution where you are collecting things at ground sampling, distance of 30 centimeter, and then some other imagery like Landsat, they are collected at hundreds of meters of resolution. Having to, align these and then compress the information in a way that you are retaining the key details is very challenging. On the other hand, on the user side, we don't all want the same things. So there is a user-dependent component that makes it difficult to come up with things that are consistent. So it's very challenging, to kind of like define what works for everyone. We often hear this saying that, there's no one size, that fits all the packaging that can, satisfy everybody. But the formats are in a way that everyone can tailor their needs in a much, much easier, very, very efficient way, so that they can prototype and build their tools in the most efficient ways as compared to if you had to download, all the data, where, again, the latency issue where you have to wait for, things timing out. For my team, we're still using the traditional format. And one of the pain points that we realized, over the past few months is the fact that when we are downloading some of the large GeoTIFF imagery, the time that you wait and the times when things time out, that means that even the partial downloaded files, they're not usable because you need to have access to the entire archive. So having some optimized way where you can just, zoom into the AOIs of interest and be able to get the data that you need is very, very, very helpful. So some of the data formats, just to highlight the last, the third item that I mentioned is you have on the first column, the formats that are coming in these cloud optimized, and then the second column is the data sets that are more traditional. So you have your cloud optimized GeoTIFFs, the COGs. Often the raster imagery, can easily be optimized as these. We'll hear on the second, from the first speaker, who is gonna talk about how, he's adapting the Zarr formats, to be able to deal with multi-dimensional raster data sets, to create some of the useful applications that can showcase that, insights and decision-making can be done in a very, very efficient way without having to, access the data in the traditional format. And some of the file formats as well, that are being adapted, it's like if you have point clouds and vector data sets, how can you map these in the cloud native architecture to be able to, ingest your geospatial data and at times even fuse with raster data sets? So this is a list of, all these different formats that can be taken advantage of in the cloud optimized data architecture. So here again, just to highlight the last column, which shows that these data sets and these formats, they're being adapted by following different standards. And a lot of these can be accessed from the OGC that stipulates, some of the consistent ways that allows for these data to be shared in ways that can be understood across the community. So with that, I'm gonna wrap up my comments here, but point out that, for those that are interested in learning more about this technology, I know that at some point there's going to be another webinar that's gonna look at a deep dive introduction to really, go over some of these data formats. But in the meantime, you're welcome to, visit the guide.cloudnativegeo to learn .org to learn more about these formats, and some of the additional references that you can also visit. I believe we're gonna put this back again at the end of the webinar so that you can either grab a screenshot now or later be able to have these references if you would like to learn more about the cloud native optimized files. With that said, I'm going to now introduce the three speakers that are going to walk us through three different use cases to help us understand and put the context in terms of these cloud optimized formats. How are they really enabling efficiency, moving away from our traditional file downloading? What are the benefits? What are the lessons and pain points that users often encounter when they are building these tools? So I'm gonna stop sharing and then go on to introduce our first speaker. So our first speaker is going to be Daniel Nwaeze, who was a data scientist at Radiant Earth and now a software engineer at Goldman Sachs. He is going to walk us through the first use case. Daniel, if you are ready, please go ahead and let me see if I...
So my name is Daniel Nwaeze. I am a former data scientist at Radiant Earth. I worked at Radiant Earth from April 2021 to August 2024, just 2 months ago. And I'll be taking the webinar use case on optimizing LandCoverNet with Zarr. So Zarr is a cloud native solution, and our focus would be on African geospatial data. Yes. Okay. So in the key topics, we'll talk about what cloud optimized is, what is Zarr, LandCoverNet, background and intro to LandCoverNet, in case if you don't know what LandCoverNet is. Then we'll talk about LandCoverNet Africa, then LandCoverNet Africa optimized with Zarr, so using Zarr for LandCoverNet Africa data. And then we would talk more about Zarr, but particularly about Zarr 3, which is a current implementation in progress that scales up from Zarr 2. So what is cloud optimized? So Dalton took a number of these. So he did a great job of taking us through what cloud optimized is. That was a really good job. And cloud optimized are basically file formats that are read-oriented to support partial reads, parallel reads, and file metadata in one read. So basically with cloud optimized data sets, you can read only a portion of the data that you want. You don't need to, unlike traditional data sets where you need to load up all of the data sets to get just one section, even if the section you want to read is very little. You need to download or load every single part of it. But with Cloud Optimize, you can just basically fetch the portions of data that you want to read. It also uses parallel reads where it can read multiple at once. So, and file metadata in one read. So with Cloud Optimized formats like with Zarr now, we can be able to know the metadata of the files. So some of these formats or some of these data sets provide functionalities for reading file metadata and knowing what exactly the file or the data set that you're working with is. And it's accessible over HTTP using READY requests. So basically, you can get cloud optimized data sets on the net, and it supports lazy access and intelligent subsetting. So lazy access, so you can you don't need to load every single part of the data. You can load the data portions that you need and work with it, and integrates with high-level analysis libraries. So for instance, with Zarr, you can use X-array, so it works with that, and you can use it for making different analysis of the data set. So we'll get to that a bit. So now what is Zarr? So Zarr is a multi-dimensional raster, so basically multi-dimensions. So it is used to So basically, it is used to represent multidimensional raster data or data cubes. We call it a data cube because it looks like a cube, and each side of the cube represents a certain dimension. So just for that. Then it is chunked, compressed, n-dimensional array. So Zarr makes it in such a way that it basically compresses the data that you load. In LandCoverNet Africa, we would see an example where it was able to easily compress the data set from the traditional GeoJSON or GeoTIFF, I think, to the Zarr format. And then, just like we said before, metadata is stored external to the data files themselves. So metadata is separate from the data files themselves. So you don't need to check the data sets to know the metadata. You can just, it's more like the metadata, just take it as more like a preview where you can just see what data you're working with. And then the data is reorganized and compressed into many files, which can be accessed according to which chunks the user is interested in. So Zarr works with chunks, so you can split your data into chunks, and then one chunk can be loaded, the next one can be loaded however you want to. Okay, sorry. Okay, yes. So LandCoverNet background and introduction. So LandCoverNet was or is a project that was developed by Radiant Earth, so probably around 3 years ago, I think. So it's a human annotated multi-satellite training data set for land cover classification. Basically, what the data set contains is millions of pixels. So it has about 586 million pixels. And it covers different zones. So we have for Africa, Asia, Australia, Oceania, Europe, North America, but our focus here is on Africa. So it basically maps each pixel corresponding to a land cover class. And we have 7 of these classes: water, natural background, artificial background, woody vegetation, cultivated vegetation, semi-natural, or permanent. And it uses 3 satellites: the Sentinel-1, Sentinel-2, and Landsat 8. So the next slide is, yes. So this is how a sample chip looks like. So you can see the chip is 256 by 256. You can see this classification app, which was used by people. That's why in the previous slide, I said human annotated. So this was the human annotated platform, where it uses a classification app where you can, with each pixel, you can classify the different land covers. And in each tile, we have 30 chips. So total, we have about 9,000 chips globally, and again, 589 million pixels thereabouts. Okay. And for the African continent, LandCoverNet Africa, I believe presently with Radiant Earth, there's a version 1.0, and it has about 1,980 chips of 256 by 256 is an annual time series data set, and about 384,000 tasks were validated by users. So there are a lot of users that human annotated this. And basically it uses I think a scoring system where it checks for different users, it checks what they labeled, one user labeled, what another user labeled, and then it maps 2 of them and checks the similarity between 2 of them to have a consensus score. So that is what this is talking about. So a consensus score where you basically know the level of similarity between the 2 or more. Then for LandCoverNet Africa now, optimized with Zarr. So this is a sample of a sample TIFF that we're using here in this use case. So this is LandCoverNet, then LandCoverNet Africa. Then under it, it has data, under the data version 1.0, 2018, which was the year that it was evaluated. Then this is a sample chip, randomly generated chip thereabouts. And then a time series instance. So remember that we said that it is a yearly time series instance. So this is for a particular snapshot within the year. Then the satellites L8, Landsat 8. Then this basically brings everything together. So this with this, then with this. So this tells us the particular date time for the chip. And finally, the band for the satellite. So you can see it's a bit bulky and a bit difficult to understand. And the file size was about 9,000 megabytes for this sample TIFF, GeoTIFF. Well, now let's look at the Zarr implementation, where you have a packaged.zr3, which is the file format of the Zarr3 implementation. And then you have the LandCoverNet Africa, and it basically brings everything together. So this chip, it brings the chip here, and then the satellites, and then the date time, and then the different bands. So the different bands are wrapped in a Zarr array called bands. So this seems more intuitive for someone to basically know what kind of data they're working with. So that is one of the advantages of using Zarr. You can easily repackage an original data set into a Zarr data set. Not just that, but it also reduces the file size. So you can see the massive difference between the two, just these two, and the file size has been reduced drastically, in this case for this TIFF. So how does Zarr work? So basically, this is how Zarr works. You have something known as the root group, which is the root of the Zarr data set. Then you have, in this case, you have a region group, LandCoverNet. So this was how the format was done for LandCoverNet Zarr format. So you have the root group, which stores the data set, then the region group for Africa. So that's pretty intuitive. Then a tile group for the particular tile, then a sensor group, Landsat 8, so the data collected from the Landsat 8 satellite. Then the date group, snapshot in time that captures the satellite imagery on this particular date, January 1st, 2018. And then the bands consist of arrays of the satellite band data, so it's wrapped in an array, in an overall group called bands. And each represents the different spectral range. So each band, for instance, here we have B01, so you can have 02, 03, 04, etc., depending on the kind of satellite that we have. And then these are really good features of using Zarr for LandCoverNet Africa. So this is an example here. I'm using Zarita, and I'm basically loading LandCoverNet.zr3 into a local store. And what I'm doing is to open the group. So basically, you can see with this, I don't need to open the entire LandCoverNet or load the entire LandCoverNet. And then after I load the LandCoverNet, do access this. I don't need to do that. When I want to get a particular group that I need, all I just need to do is just specify the path that I want, the path of the group that I want, and then it loads the group. And then for the array, it's the same thing too, but basically loading the bands for the array. So that way I can easily just access the set portion of the data that I want instead of just accessing everything, and after accessing everything, now try to find out which certain portion of data you want. So you can also create groups and arrays, just like how the Zarr LandCoverNet was done. All you just need to do is just to replace this with create, and that's all. So that's a use case. And then arrays. So Zarr, remember that we said that Zarr consists of metadata that shows you what the group or what the file is all about. So in this instance, we have an array metadata that shows the metadata of the array pretty much. So it tells you the shape of the array that you're working with. So this is 256 by 256 and 7. So 7 different bands here. The data type, the chunk grade. So basically these are the chunks. So for each band has a particular chunk. And then attributes, you have the sensor here, sensor band. So this tells you all the bands in the sensors. Then dates, the Zarr format, and the node type. So this way you don't need to try to figure out what is in the data. All you just need to do is just to check the metadata, and you can be able to know, okay, these are the sensor bands I'm working with, this is the sensor I'm working with, this is the date time, etc. Which is very good of Zarr. And just like we said before, the Zarr features just on a general scale, chunking where you can just access specific portions of the data and natively supported in Python. So you can use analysis libraries like Dask, XArray for data analysis, and ML. So you can integrate data into existing data science workflows. and interoperability. So we have a range of different tools and libraries, just like the ones we mentioned before. And flexible data structure, so it doesn't need to be rigid. So Zarr creates a flexible data structure where you can specify the structure of the data that you want. It doesn't need to be something that should be rigid. So if I instead just want arrays of 5 bands to create instead of 7 bands, I can just easily tell Zarr to create that for me. And of course, cloud compatibility with cloud-based storage systems. So in this previous example here with local store, there's a way that you can specify if you are loading from S3, you can specify the S3 parts that you should load the data from. So very compatible. Then these are the important features of Zarr 3. So with Zarr 3, you have a hierarchical metadata. So I'm not sure if Zarr 2 has the metadata feature I was talking about, but I know Zarr 3 definitely does because LandCoverNet Africa was done with Zarr 3. Then it also has key value stores where you can have a key and then basically like the way S3 is. So it has the metadata storage where you have the key, which is the metadata field, and then the value, which is what the field is. So that's it. Then multidimensional chunking and layout flexibility. So with Zarr 3, there's more flexibility in how you lay out chunks storage backend. So you can have multiple chunking strategies. There's no one giving way to do it. So it offers a very good flexibility in how you want to arrange or structure your data. And of course, it also allows greater flexibility in defining the storage layout. So how you want your arrays to be distributed across different storages. So it's really good especially when you're working with large scale cloud native geospatial data sets like LandCoverNet that is very huge. I can't remember how huge it is, but it's very huge. So that's I think questions will probably be at the end. So that's the end of my presentation. I hope this was helpful.
Thanks so much, Daniel. That's a very insightful kind of like summary around Zarr. Really appreciate it. I know there may be some questions from participants. So the way that we're going to do this is that when all the speakers are done, we'll have a panel that will take your questions. So I advise you that you either ready those questions now, put them in the Q&A, or you can hold off, write them down somewhere, and then when you get to the panel session, we can take your questions. With that said, we're going to move to the next two speakers that are coming from Digital Earth Africa that are also going to share additional use cases. The first speaker from Digital Earth Africa is going to be Mpho Sadiki. Mpho, if you're ready, if you can go ahead and share your slides. And again, feel free to do an extended introduction of yourself and your work. Thank you.
Thank you very much, Dalton. Hello, everyone. My name is Mpho Sadiki, and I'm an Earth observation data scientist for Digital Earth Africa. And today I'll be taking you through the Digital Earth Africa crop type mapping workflow, which we consider an end-to-end workflow for food security. But before I do that, I would just like to also set the scene by introducing Digital Earth Africa, what Digital Earth Africa is, and which will hopefully help you understand the work that I'll present, as well as my colleague Victoria after my presentation. So Digital Earth Africa's vision is to provide a routine, reliable, and operational service using Earth observations. We aim to deliver decision-ready products that empower policymakers, scientists, and the private sector, as well as civil society, to address social, environmental, and economic changes on the continent. By doing so, we're fostering an ecosystem of innovation across various sectors. And we concentrate on several key thematic areas, which include land degradation, coastal erosion, urbanization, water resources and flood risks, agriculture, and food security. Digital Earth Africa is built on the Open Data Cube infrastructure. So the Open Data Cube infrastructure is a free open source software package that simplifies the management and analysis of vast amounts of satellite imagery and Earth observation data. It enables users to easily access, process, analyze decades of geographical data to track changes on the Earth's surface over time. Within the Digital Earth Africa Data Cube, we house both raw satellite imagery or data as well as derivative data products. And one of the standout features about the Digital Earth Africa Data Cube is that it represents the largest global implementation of an open data cube, entirely cloud native and hosted on Amazon Web Services on simple cloud storage. The setup allows for free public access and provides a continental scale satellite archive that can easily be navigated. Our data products are completely free to use, even for commercial purposes, and they are optimized for cloud processing. In fact, considering that most of our data is raster data, it is available as cloud optimized GeoTIFF files, and those are GeoTIFF files that are designed for efficient access and processing in cloud environments. Unlike traditional GeoTIFFs, which are typically read and processed locally, cloud-optimized GeoTIFFs are structured to allow users to access specific portions of the data without downloading the entire file. And this is made possible by internal tiling and overviews, which divide the image into smaller, manageable chunks and include multiple resolution levels as well. And these cloud-optimized GeoTIFFs are particularly beneficial in cloud-native workflows because they minimize the data transfer costs and speed up processing by loading only required parts of the file, which makes it ideal for large-scale geospatial processing. This is just an example of some of the continental scale services that we create in-house in Digital Earth Africa, and these are actually very important to the workflow that I'm going to present as well. But I would just like to highlight that some of these include the GeoMed service, which is a cloud-free composite of satellite imagery compiled over a specific time frame. We have them as annual geomedians, semi-annual geomedians, as well as rolling monthly geomedians. There's one of our popular products, the Water Observation from Space, which uses satellite imagery, specifically the Landsat Archive, to provide a historical view of surface water across Africa, showing where water is typically present, seldom observed, or where inundation has occurred. We also have the Coastlines Monitoring Service, which is a product of ours that maps annual shorelines as well as rates of change to track coastal erosion and growth using satellite imagery and tidal modeling. There's others that include fractional cover, cropland extent, and the Waterbodies Monitoring Service, which my colleague Victoria will be taking us through after my presentation. Another important thing is that Digital Earth Africa is more than just a platform for satellite data. It is a continental scale initiative that is designed to activate a community across Africa by improving access to Earth observation data. And we do this through partnerships with local governance and in-country expertise, where we build sustained capacity across the continent. And through these partnerships that we can see here on the map, we're able to effectively make sure that our data is available and is being used across the continent. And the workflow that I'm about to present is a perfect example of how we're leveraging this wide community on the African continent to meet and co-develop solutions of setup that meet unique African needs. This workflow that I will start going into detail now was developed in partnership with the Regional Center for Mapping of Resources and for Development, RCMRD, in Kenya. It was created for Zambia, but it was later scaled to other countries through collaborations with AgriMet in Niger and the FAO in Rwanda and Mozambique. So the whole idea around the crop type mapping workflow was to create an end-to-end workflow that allows users to collect crop type data, train machine learning algorithms, and use those models to create accurate crop type maps for their regions. The technology behind this workflow is the Digital Earth Africa Sandbox, which is a cloud-based computational platform that operates through a Jupyter Lab environment. It provides a limited but still free compute resource for technical users to explore the Digital Earth Africa Data Cube. So that is the almost 5 terabytes of data that we have available. And within this environment, you're able to query the data for an area that you're interested. And that is what this crop type mapping workflow showcases the fact that we're leveraging those continental scale data sets that we have at local scales, and in this case, at country level. In addition to the sandbox, the workflow incorporates tools for statistical sampling, like the ECAS ODK for field data collection and cleaning. And like I said before, it was co-developed with with some of our partners who we consider to be part of the Digital Earth Africa product development task team. So the workflow, as I said, is designed to be used in the Digital Earth Africa Sandbox, where you have access to the several continental-wide analysis-ready satellite datasets and derivative products. The workflow is provided and made freely and openly available to everyone as a collection of documented Jupyter notebooks that are available in an open GitHub repository, along with a copy of the data and supplementary files required to run the workflow for Central Province in Zambia. And so this is just to ensure that a first-time user can actually run the workflow as is and learn how it works before they can use it in their area of interest. The workflow has 5 key steps. The first step is, of course, the sampling of the data. And this is initiated by creating a sampling approach to ensure that we collect a representative data, ground truth data. And this is very critical for training accurate models. And the second step is to actually go out and actually collect that data. And then we come back into the sandbox and we use the Digital Earth Africa platform and tools to identify the most relevant features for building machine learning models with the power of the sandbox. And then we do the model development, and then we train the models and actually type the crops on the ground. So this graphic here gives us an in-depth description of what the notebooks actually look like. As you can see, the first notebook looks at, the first step rather looks at sampling design. And this is actually something that is achieved over 4 notebooks that help you create a representative sampling design using stratified random sampling. The stratification was done in this case at 2 geographic levels. First, the number of samples taken per district was based on the proportion of cropping in that district compared to the total cropping in the province. Second, the number of samples per cropping class in that district was based on the proportion of the class to the total cropping in the district. And to identify classes to sample from, we used one of our continental product, which is the Digital Earth Africa Crop Mask, to identify these cropping areas, and then fitted a K-means classifier to satellite imagery from the Digital Earth Africa Data Cube to extract features for these areas, so including spectral bands from Sentinel-2, as well as some vegetation indices like NDVI, also incorporating Sentinel-1 radar backscatter, and our other product, the fractional cover measurement from Landsat. After collecting the data from the field in step 2, we come back into the sandbox, and this is where we start to see the power of cloud computing, because after you've prepared the data, making sure you've removed any data that is has missing values, making sure your crop type are specified properly, you move on to the feature extraction. The feature extraction and the exploration here is managed by 2 notebooks, which involve extracting relevant features from satellite imagery, which will be used as input for our machine learning models and exploring and understanding the features to optimize the models. For our feature space, this consisted of Sentinel-2 geomedian products at 3, 6, and 12 months period, Sentinel-1 geomedians, Landsat fractional cover, chirps, rainfall averages, and SRTM model slope. In total, this resulted in 113 unique features that can be used to actually type the crops on the ground. This is possible because we're working in a cloud environment that allows us to have access to a large amount of data, but also have the ability to query what we need for the area that we're working in. And of course, thereafter, we move on to the machine learning, where we train and estimate the performance of the models, and then move on to the classification of the crop types on the ground. So this is just the general, or rather a high-level overview of what that crop type mapping workflow does. And this is applicable to any part of the continent because we are leveraging already existing satellite imagery and derivative products that we have hosted on the Digital Earth Africa platform. And we also make available the sandbox, the cloud computing environment that allows you to actually run these for any part of the continent. So I would just like to say, although crop type mapping is not a new technology, it has always been difficult to scale. And the fact that we now have the ability to develop a flexible workflow through open and free through an open and free platform, and also leveraging our partnership network, it just shows the power of cloud native geospatial data and the ability to scale and also transfer to different parts of the continent. And as you can see, our continental products here act as a shortcut for efficient workflows because we've created them beforehand. All of Africa has access to them. All you need to do is go out and actually get the ground data and come back and already have all the data pre-processed and ready for you. All you need to do is query for your area of interest. Thank you very much for your attention. And I'll look forward to the questions at the end of this session. Thank you.
Thank you so much, Mpho. That was a very insightful, case study, and the way that you kind of just narrated this from, of course, data formats, but also to see the impact in terms of, okay, what is the benefit toward the analytics, workflows, which I presume a lot of people are more interested in terms of, okay, you have the data, but how do you get it, to be of use into the machine learning workflow? I'm sure there's many questions from the, participants. So keep those, getting posted on the Q&A. When we get to that stage, I have, few of my own questions that got triggered from your presentations. But before we jump to that, we have one more presentation, and that is also coming from Digital Earth Africa. Victoria Neema is gonna talk to us about, monitoring services for water bodies. And I think that's something that also kind of complementing what we just had from Mpho. If you are ready, Victoria, please go ahead and share your slides. And feel free again to introduce and expand, the intro of your work the same way that the others did. Thank you so much.
I was just starting off from where Mpho had done the introductions. So Africa being an cloud-based open data cube deployment, we are able to scale our workflows, like she said, from local to continental, to producing continental services like the water bodies monitoring services. For example, the crop type workflow eventually translate to generating the 2019 cropland extent mask that we currently have on our platform as one of the continental services that we provide. Same with the water bodies monitoring service. We usually prototype on our sandbox for smaller areas of interest before eventually scaling up and producing a continental-wide service. Now, the water bodies monitoring service is a collection of over 700,000 water bodies that we've managed to identify from the water observations from space all-time summary product. And the surface area change for these water bodies is derived from the water observation from space feature layer product. These two products, the historical extent and the surface area change, are what now make up what we call the water bodies monitoring service. I'll start off by talking about the product. This product is a polygon-based view of the water observation from space all-time summary product. And how we derived the water body polygons is we define them as being a set of pixels that are classified as wet in at least 5% of clear observations since 1984. And then added a second filter where for these polygons to be retained in the product, they must also include a set of pixels that were classified as wet in at least 10% of clear observations since 1984. We specifically define the water bodies in this way in order to select both permanent and seasonal water bodies while ignoring highly regular flooding events. Through this, we've been able to identify, like I said, over 700,000 seasonal and permanent water bodies, with the smallest water body being at about 5 Landsat pixels. So that was about 4,500 meters squared. These water body polygons are not a capture of the true extent of a water body for any given year, but through the thresholds that we've used, we're able to capture the maximum extent a water body has been across time since 1984 to 2022. On screen is just a brief diagram on how we go about deriving the water bodies historical extent. As you can see, the bounds for these, like the boundary of the extent that we have covered is defined by the Hydrosheds version 1.1 landmask. This is specifically so to prevent including ocean polygons in our historical extent. So we want it's completely just for inland water bodies. We also have on the right the attributes that are included for each of the water bodies that we've identified. So they have 2 unique identifiers. One is the UID is a geohash of the centroid of the water body polygon. Then the WID is an integer derived from the geohash. Water bodies that are close in terms of the WBID tend to be near each other. So that's a good way of being able to get like proximity of different water bodies together to each other in the product. We also provide the area, which is the measured in meters squared, the length of the water body, which is the longest side of the water body, the perimeter, and of course the geometry of the water body extent. Moving on to the surface area change product. Now this gives the time series for the water surface area for a single water body. This is given in proportion to the historical extent. Like I said before, is not the actual area, but the largest the extent that a water body has been. An important caveat in this is that for you'd notice in the attributes that I'll show in the next slide is that we have included the invalid percentage, where invalid is defined as when the classification from the WRF's observations, the shorthand is WRF's, WRF's feature layer seen, was not able to classify a pixel as either wet or dry for a single water body. So that's where the invalid comes in. And then from the invalid, you're able to say a valid observation is when for a scene, we were able to capture 85% of the historical extent in a single day, and the invalid percentage of that observation was less than 10%. This is to enable us to give a reliable percentage measurement of both the wet and dry coverage. On screen, you can now see the attributes that we provide. for the surface area change, and also a diagram showing how we derive these measurements. We provide the date of the observation, so that would be the date of the WAF's feature layer seen that we derive the measurements from. We also provide the area as both a percentage of the historical extent and also the actual area that was classified as wet. We do the same for the dry, where we have the percent dry and the area, and then we also have the invalid percentage from the definition that I gave beforehand. To be able to see and make use of this product, we have it available on the Maps platform, which is our main visualization platform, where you can just load the data and view it. This is where I got the visuals that you've seen in the previous slides. And we also have the analysis sandbox that Mpho mentioned before, where you can use our notebooks in. And we have a notebook specifically for the water bodies dataset, where you can load the polygons loaded from the WFS service that we have, and you can also load the time series for a single polygon that we have provided through an API. Again, being in one of the principles of Digital Earth Africa is that we provide open access to our data and our methods. The code that was used to derive the water bodies is available in the repository on screen. You can use it to sort of add on your own analysis if you'd like to test it out. And the Africa Sandbox also provides all the notebooks that we use for the data sets, and also some of the use cases that we have done that use the water bodies service. I'll end it there for now. Thank you so much for the time.
Thank you so much, Victoria. It's a very insightful talk. So as I mentioned at the beginning, well, the middle of our discussion, our talk, this is now the segment where we invite questions from the participants. I can already see there's quite a few questions that we already have posted here. So to kick us off on the Q&A panel, let me toss this question, to all three of you. I'll try to combine one of the questions that I saw in terms of, the lessons learned, in the process of putting these technologies together. So starting with Daniel, from your description of, getting the traditional file formats, mapping these into Zarr, could you highlight a few of the challenges that are kind of like, commonly gotchas, to help our users understand and appreciate, especially for those that are looking at, adapting some of their workflows to use these technologies? What are some of the pain points, that you'd highlight, as common traps, and how did you go about, circumventing these in your workflows?
I think the first thing is when you want to start creating those things, so don't just go and start coding or start converting them. You need to first map out how the data set looks like, what you want to achieve. Because when I started it, I was just going straight ahead, okay, let me try to convert this to this. And then I encountered an issue because these cloud optimized formats, they are good, but the other thing is they are not very used as much. So it means that they don't have so much documentation and so much support, and you need to be careful when you're working with them. So if you don't know what to do, you would definitely have an issue with it. So the first thing is make sure you have the right documentation that you need. Go through the guides. A number of times, all these things, there are not many, because since these technologies are new, so not many people have so many issues that they post online. So if you encounter issues with them, you most likely, there's a good chance that you won't really find what you're looking for, which is why it is important for you to know what you are doing. because it is when you know what you are doing and you experience those errors that, okay, you can debug those things. You can say, okay, this is what I need to do different. This is what I need to change. So that understanding of, okay, I want to do this. I want to convert this to this. I want to use cloud optimized formats, but I don't just want to use it blindly. I need to know what I'm doing. I need to know why this format is used. So know why you're using Zarr, know why you're using the rest, know why you're using Geospatial, all of that. When you know all those things, it would get easier for you to do that. So I think I had that issue first when I didn't know why I was using this and I didn't know what to do. And I was just putting everything together and it was a mess.
Thank you so much, Daniel. I think what I'm hearing here is that there is a potential gap or need for training. So I'm going to take that point and I'm going to rephrase it for Mpho and Victoria. First of all, Mpho, if you can respond in the context of the challenges that you encountered. There's a question that we got from one of the participants who actually counted 9 countries on one of your slides. And the question was following one of your comments in terms of activating a continent-wide community. This is a participant who is coming from Zambia. They want to know what challenges you faced in expanding, your reach in terms of making the service available beyond just those, if you were to make it beyond those 9 countries. So in that context, if you can respond to the question that got triggered from Daniel, what is Digital Earth Africa doing, beyond the partnerships to introduce training or tutorials to help some of those participants that may not be technically savvy to be able to learn things by themselves? Are you running workshops across the continent, tutorials? How is that being executed, if there's anything of that form?
Yeah, that's a very good question, and it's very relevant for Digital Earth Africa and how we aim to operate on the continent. So those 9 countries that are actually highlighted there, they're not necessarily the partners that we restrict ourselves to work with, but they're what we call our implementing partners. So together, these countries are mandated to work across a lot of the countries on the continent. So they help us to make sure they push the Digital Earth Africa mission and the data sets and the usage of our products in the different countries. But we are 100% open to working with anyone on the continent, be it a student, an academic institution. But right now in the phase that we're in, our main focus is to get into government. So we're trying to get into government departments and have them leverage the power of Earth observation for the continent. And the one thing that we do see as a barrier is the unwillingness to shift from more traditional, GIS based approaches to problems. Using your QGIS, your ArcGIS, and your more traditional sense of you doing it over smaller areas instead of and when we come in with the idea of the ability to scale and reducing that time constraint and reducing the need to download, it takes a lot, because also we're coming with the sense, with the idea of coding in Python, and people are like, oh, Python is so scary. We don't want to get into that. But Digital Earth Africa actually offers a lot of capacity and development. We have a whole team of capacity and development and user engagement. So if you're interested in us coming to where you are at a university, at your organization, company, wherever it is, we go anywhere to teach people how to use our products and services. And we also have live sessions that we host every Wednesday at 11 a.m. GMT on Zoom, where we have them in English and French alternating, where we go through a lot of the work that we have available in the Digital Earth Africa platform. And this is available for anyone to use to join and ask any questions, and also contact us in the science team, for instance, myself or Victoria, to assist you in any of the work that you might also be doing.
Thanks, Mpho. Victoria, do you have anything to add to that?
No, I think Mpho has covered it quite well.
Okay, thank you. Let's move on, and we'll take a question from the audience. So I think there was a follow-up to Mpho's presentation, again, coming from the same participant from Zambia. The question is, can you speak more about the sandbox that you mentioned? You highlighted a use case in Zambia. I think they wanted to know more about the sandbox. Is there anything that you can share with the listeners, Mpho?
So I want to just get a link that I can drop into the chat for everyone. Let me just make sure I'm sharing with. I don't think I have the ability to share with everyone, so I'll try type the answer in the Q&A and send that through. So Digital Earth Africa has multiple ways that you can interact with our data. One of them is the maps, which is a visualization tool that Victoria showed. But where most of our science happens is the sandbox. So this is a cloud-based computational platform that we have that operates through a Jupyter Lab environment. If you've ever used Google Earth Engine, it's that type of infrastructure. So we give you free compute and you have direct access to the Digital Earth Africa data cube. And also you have direct access to the science team for assistance should you have any issues with that. So it's just a cloud-based computational platform that we have. And in there are hundreds of pre-written notebooks that we've worked on for a lot of different cases that you can apply anywhere on the continent by just changing a location, changing some dates, changing some of the data that you're pulling in, and improving on those notebooks as well by pulling in some of the data that you have or improving on the analysis as well. I hope that helps.
Thank you. We'll move on to the next question. I think this is pointed to Victoria. One of the water bodies attributes. Yeah. So the question was more on, are these standard features in literature? The user, the participant was curious to learn more about how you have arrived at the features that you listed or the attribute that you listed during your presentation. Are these commonly used across the community, or are these kind of like, I mean, you know, Digital Earth Africa informed, but I'm assuming, you know, through the partnerships, these are adapted from the community, but you can speak to that. Yeah.
So our continental services, like Mpho had mentioned, are co-designed and co-developed with our implementing partners through what we call the Africa Product Development Task Team. And we realized that these are the most common questions about water bodies that our partners who are using the service wanted to know. So that would be what's the area, what's the length, perimeter, also surface area change, what would be the percentage of the water body that's currently wet at a particular day that it was observed. So these are the common questions that our users or our future users had at the time.
I see. So are there any standards? I mean, just follow up on that. Are there any standards that are gonna come out, you know, something that you are going to kind of like prescribe to the community as a benchmark, like going forward, if anybody else outside your partnership is looking at, you know, running similar workflows, could these be adapted as references for doing the same type of workflow?
Yes, we are happy to have that our work to be adapted in that sense, which is why we have the code that was used to actually develop the service is open access in the repository that I pointed out in one of my slides. So any of the users or future users can pick up from that point and add on any other attributes that I think are important to be included. Also, if we are open to partnerships and improving this service, I think I forgot to mention that this is still a beta service, so we still looking at users to validate and continue giving comments or contributions in how to make the service better. So if they feel that other attributes would be important to include in defining a water body, we are open to hearing that and including that in future iterations of the service.
That's very helpful. Yeah, I was going to ask you a question about, what is the feedback mechanism that you are soliciting from, users outside your partnership? But I think you spoke to that point in your comments. So
yes, we were happy to partner with others. Thank you.
Yeah. Thank you, Victoria. So moving on to the next question. This is a question from, I think, Alice, asking about how are these data sets collected? And I'm assuming these data sets, meaning the data that you presented, Mpho. Can you give an idea of the parameters of the data sets, for crop monitoring?
Is this in relation to like the training data, or is it the data, like the data we have available?
I'm assuming this is all of the above, but maybe you can contextualize in terms of training data, because for training data, right, you don't just create the data. You talked about sampling, and I'm assuming there's some diversified strategies that you employ to make sure that you have that representation that spans across different areas of interest, and also to position your machine learning to be able to generalize and transfer across other parts where you're not collecting data. How are you going about doing that? And what is kind of like, should I say, as you look through the different characteristics of the modalities or the sensing modalities, on the imagery, how are you kind of like balancing to make sure that you have equal representation so that you can learn better models?
Okay, so let's start first with the gathering of the training data. I did explain that as part of the workflow. I think Nwaeze has shared that the GitHub repository that has the workflow. The first set of notebooks help you come up with that strategic approach to sampling, instead of just going out into the field and just generally sampling random points, but rather you do leverage the Digital Earth Africa crop extent map to first identify areas that are cropped and then stratify those into suitable areas to sample. And then afterwards, in this case, we use the ECAS ODK technology to do the sampling, but I'm pretty sure you can go out into the field and use whatever sampling tool you'd want. You could probably even just use a GPS and gather the points. All you need is just points that you can bring back into the sandbox. And in the sandbox, we do this process where we buffer, instead of just using points, we buffer the points by 15 meters, so we can actually extract the features for those points to be able to train the models. And in the workflow, when you go through it, you also see there's a lot of work that goes into selection of the features that are subsequently used for the final model. There's a lot of work that goes into making sure that the data is not too correlated and all of that stuff. So there's a lot that goes into feature selection as well, and that can be explored in the workflow. And of course, the workflow is completely adaptable. Not everything that we give you is not that you just have to use it as it is. You can always come in with your own ideas of subsetting those input features as well. So I think that's what I would say about that.
Yeah, I think that speaks to, the training data. If the question is not answered, Alice, feel free to post and clarify which data. So to move on to the next question, I'm going to point this to Daniel. Looking at the cost effectiveness, of compressing the files, moving from the traditional, file formats, to Zarr or, Geopacker, types of files. So compression often comes at a cost of losing information, right? I think you kind of like touched on this a little bit. Could you speak to the trade-off in your example, you had that almost 9 meg file that was compressed to like, almost 1 meg, that GeoTIFF. For certain applications, if you lose the details, then, the benefit of actually moving to, the cloud optimized format, kind of like, disappears, right? Do you have some examples that you can share in addition, that point into where you see this trade-off not being of benefit, meaning that you're better off just doing things using traditional file formats?
Or in this case, so where they are the raster was GeoTIFFs and the arrays were in regular, I think, NumPy arrays. So in this case, I don't think we noticed any much trade-offs, because what it basically did was just to pick out the points, the pixel points, and then convert those pixel points to arrays. So I think the main reason why the previous one was was that much was because it was storing a lot of unnecessary information. So there's some information from the original LandCoverNet data that we didn't necessarily need. Some information was also duplicated in the folders, in the file folders. But with Zarr, we could just specify the unique ones that we needed. So once we have unique elements, all we just need to do, Zarr will automatically know, okay, this is what I need to do. These are the arrays that I need to get. I don't need to do any duplication. So that was a major reason why the file size decreased drastically. But besides that, I think the array was also lesser than the original GeoTIFF. But I didn't notice any considerable, I mean, there was a tiny bit, but not a considerable difference between the quality of the two data. So I think that's why Zarr is really good, because it compresses the data into the formats, into a lesser formats.
Okay, maybe the same question, thanks, Daniel. Same question to both Mpho and Victoria. Are there any benchmarks that you have that are out there that compares some of your machine learning workflows that are executed on traditional file formats compared to, the cloud optimized files that you're leveraging on your platform? So kind of like, looking at, okay, apples to apples, you're running the same data set, for crop monitoring. Let's say you have your 100,000 samples, uncompressed version, and the, compressed cloud format. The models, when you do the testing, what is the evaluation that shows us, that the models are performing well? They're performing consistently. However, of course, in the cloud environment, things are much more efficient, and the storage is also optimized, to take less space. Is there something that you have that's out there to compare the two?
I'll go first, but to be honest, I would have to admit that we almost operated in a blind spot, because we were, as Digital Earth Africa, it was, created to be a cloud native solution. We almost operate without the thought of what is happening if you were to analyze these data sets at a local scale. For us, cloud native is the be it and end all of all that we do. We're just trying to push the scalability and the efficiency that it has to offer. So I wouldn't say I've seen any benchmarks or any comparisons that have been made to actually see if the work that is being done in the cloud is comparable to what is being done locally. Perhaps Victoria has a different take.
For the machine learning workflows, like Mpho said, we've not done any benchmarks, but what I can speak from experience is because of how the data cube works, where we're able to index these data sets quickly, since they're hosted on S3 buckets. I would speak on load times. I have run workflows, not machine learning workflows, but just regular analysis, where I've had to for a specific area of interest and a time period, I have to get data sets directly from wherever they are. Like, so the searching process by either time or area is quite lengthy as compared to when we have the data sets already indexed in the data cube, and all I need is from the data cube load function is to point latitude range and time range, and takes a couple of seconds, and I'd have the data that I need ready to work for whatever analysis that I need to work on. So what I can speak on is faster through the data cube, is much faster load times.
Thank you both. Lisa, I see we have 4 minutes left, for the webinar. I would like to give our panelists maybe a minute each, for closing thoughts. If you each could highlight, how participants can stay in touch with you, I think that would be helpful. There might be, extra questions to follow up with. So any contact info that you can share with participants in your closing comments will be helpful. We can start with you, Victoria, your 1 minute, closing thoughts, and then we'll go to Mpho and then Daniel.
Sure. So you can reach out to us. You can view our website, digitalearthafrica.org. For the sandbox, it's sandbox.digitalearthafrica.org, where you can log in, create an account, and start off using our workflows and the data sets. Earlier, there's a question on training. We also do provide courses on how to use our platforms. On our learning platform, you'll see it on the website. The major course that we have is like a self-paced course that you can get a certificate after it, and you'll be able to comfortably use our platforms after that course. I think that's it from me.
Thank you. Over to Mpho. Thank you.
Yeah, thank you. So first, I'd just like to say thank you for giving us this opportunity and having the two of us from Digital Earth Africa come and present. So Digital Earth Africa is completely open and available to collaborate with anyone on the continent. So if you do want to reach out to us, as Victoria pointed out, go to our website, join our live sessions as well, sign up for the sandbox. It's a pretty exciting place to be. And if you have any questions, please do reach out to us and we will assist you in any way that we can. Thank you.
Over to you, Daniel. Thank you, Mpho.
Okay. So you can reach out to me on LinkedIn. So I posted my LinkedIn link in the chat. So if you want to reach out to me, I'm always available on LinkedIn. I use it a lot. If you want to reach out to me on email, you can reach out to me to maybe Lisa can share that if there's the opportunity to, but I prefer LinkedIn because I can easily see messages and reply to them.
Well, with that, thank you so much. It's been a pleasure on my part to moderate this session, to listen to all three of your works. You're really doing some of the great work that's showcasing the impact of how these technologies could be adapted by others. I'm sure there will be many more to follow, after this discussion.